Hey everyone and welcome. Today we're diving into a really cool concept in biochemistry, why a simple sugar like glucose isn't nearly as simple as it looks. You see, in a solution, it actually has two different identities, and the story of how they flip back and forth is absolutely central to everything from how we digest our food to how we diagnose diseases.
So that's the big question, right? How can one single molecule have two distinct identities? It's kind of like a chemical secret agent. To figure this out, we need to take a close look at what happens the moment a sugar like glucose hits the water.
All right, here's our game plan for this explainer. We're going to start with how sugars curl up into rings, then we'll meet the two identities, we call them anomers. After that, we'll watch them do a little dance called mutarotation, figure out why any of this matters biochemically, and finally connect it all back to medicine. Let's get into it.
Okay, first up, from chain to ring. Before we can understand the two faces of glucose, we have to see what shape it takes in a solution. And spoiler alert, it doesn't stay in a straight line for long.
So, picture this. When glucose is in water, that straight chain form is actually pretty unstable. The aldehyde group way up at carbon 1 is super reactive, and it's basically looking for a partner. It finds one in the hydroxyl group down at carbon 5. When they connect, the whole molecule just spontaneously snaps shut, folding itself into a much more stable ring.
And this new ring structure, it's got a special name, a hemiacetal. Now the key thing to get here is that this isn't just a simple change in shape. The act of closing this ring creates a brand new chemical feature right at carbon 1, and that spot becomes the absolute epicenter of our whole story.
And that leads us right into our second section. It's time to meet the main characters, the anomers. These are the two different identities that are literally born from that ring-closing reaction we just talked about.
So what exactly are anomers? Well, they're a type of stereoisomer. That just means they have the exact same chemical formula, but a different 3D arrangement of atoms. And the key difference, the only difference, is at one very specific spot, the anomeric carbon. For glucose, that's our old friend carbon 1, the one that used to be the aldehyde.
And check this out, the difference between them is incredibly simple. In what we call the alpha form, the hydroxyl group on that anomeric carbon points down. In the beta form, it points up. That's it. That's the entire distinction, just up versus down. But as you're about to see, this tiny little change has massive biological consequences.
And to help you remember this, here's a great little mnemonic that's super helpful. Alpha is down, beta is up. Mutarotation mixes them up. Keep that little rhyme in your head as we move on.
Which brings us right to the mixing up part, the mutarotation shuffle. You see, these alpha and beta forms don't just pick a side and stay there. Nope, they are constantly in this dynamic little dance with each other.
This dance is officially called mutarotation. It's the spontaneous process where alpha and beta forms are constantly flipping back and forth in solution. And this goes on until they finally reach a stable, predictable balance, what we call equilibrium.
So how does this shuffle actually happen? It's a three-step move. First, the ring has to briefly open back up into its straight chain form. For just a split second, that aldehyde group at carbon 1 is exposed again. Then, when the ring snaps shut, that hydroxyl group has a choice. It can lock into the down alpha position, or it can lock into the up beta position.
Now this dance doesn't end in a 50-50 split. Not at all. At equilibrium, you'll find that about 2/3 of the glucose has settled into the beta form. Why? Well, it's just a little more stable. With that hydroxyl group pointing up, there's less crowding. And get this, at any given moment, less than 1% of the sugar is actually in that fleeting open chain form.
Okay, so we've got alpha and beta forms doing their little shuffle in a solution. But who cares? Why does any of this actually matter? Well, let's jump into section 4 and see how this tiny change leads to a huge biological impact.
It turns out this whole alpha versus beta distinction is absolutely critical in at least three major areas: a sugar's reducing properties, how our enzymes recognize them, and how they link together to build bigger molecules. First off, remember that brief moment when the ring opens during mutaration? That split second exposes the aldehyde group, and it's that free aldehyde that makes glucose a reducing sugar. This property is exactly what allows it to react in diagnostic tests like the Benedict's test, which has been used for ages to detect sugar in urine.
And here is the most dramatic, most mind-blowing example of why this all matters. Starch and cellulose are both just long chains of glucose. The only difference between them is the bond.
Starch is made of alpha-glucose units, and our digestive enzymes are perfectly shaped to break those alpha linkages for energy. Cellulose, on the other hand, is made of beta-glucose, and that single, tiny change in orientation makes the bond completely unrecognizable to our enzymes. The result? Starch is food, cellulose is indigestible fiber. The entire difference between energy and structure comes down to that one little up versus down bond. It's incredible.
And that brings us perfectly to our final section, the clinical connections. Let's see how all these concepts actually play out in real-world health and medicine.
So you can really see how it all connects clinically. Our ability to digest our food, that hinges on our enzymes being super specific for those alpha linkages. The way we screen for diabetes, that often relies on the reducing property that only exists because of mutarotation. And in certain metabolic disorders, the entire system can break down if the enzymes that manage these sugar conversions aren't working right. It's all just a beautifully interconnected system.
All right, that was a lot of information. Let's do a quick fire quiz just to help lock it all in. Ready? First question, which carbon becomes the anomeric carbon in glucose? That's right, it's C1, the original aldehyde carbon.
Next up, which anomeric form is more stable and more common at equilibrium? You got it. It's the beta-D-glucose, making up about 2/3 of the mix.
And finally, we can digest starch because our enzymes are built to break what specific type of linkage? Exactly, the alpha-1,4 glycosidic bonds.
And that leaves us with a final thought to chew on. We've seen today how the simple up or down direction of one single bond can be the difference between energy and fiber, between food and structure. It really makes you wonder, what other tiny biochemical details like this are out there, quietly shaping our entire biological world? Thanks so much for joining me.